Now, the other thing that these conjugated dienes can do is they can undergo an interconversion. So if we look at this, we have a trans, right? We can kind of imagine these double bonds being trans to each other here, and then we can imagine them being on the same side over here. So this arrangement is called S-trans and S-cis, and this occurs at room temperature. So one of the things that we're going to see, and it doesn't really apply for a couple of pages here, but one of the things that we're going to see is that for a specific type of reaction that we see in this chapter called a Diels-Alder reaction, that this S-cis conformation is required. So kind of store that in the back of your mind, and we'll come back to that in our next lecture when we hit Diels-Alder. Well, let's talk a little bit about allylic positions and stability and some of the reactions that we're going to see in this chapter. So just as a little review, an allylic position is a position that's adjacent to a carbon-carbon double bond. So that position that's highlighted right there with the arrow pointing it to it, that is the allylic position. Again, adjacent to our double bond. So that tends to be a stable position for radicals and for carbocations because of resonance. So if we look down below here, we're going to see those little fish hook arrows again. So what you might see is something like this radical forming here. Right, so you might see a radical forming there, and then this would give us the following resonance structure. Right, so remember we use those fish hook arrows to show the flow or the movement of electrons for a single electron here. Now, because of that resonance stabilization, allylic radicals are more stable than tertiary radicals. And we mentioned that last semester, but if we look at a primary radical versus a secondary radical versus a tertiary radical versus an allylic radical, we can come up with some numbers, and you don't need to memorize these numbers, but they're important because they show the trend here. So here, again, primary, secondary, tertiary, and allylic. All right, so if we look at our energies of these, our BDEs, you get 98 kcals per mole. This is 95 kcals, 91, and 87. Right, so as you come down here, you can see that allylic position is even better at forming radicals than a tertiary position. All right, now, what about carbocations? Well, same thing holds true for carbocations. Not the energies necessarily, but the stability. So, looking through this, here you have a positive charge. Usually we'd circle that guy. Right, and showing the electron flow here, we're using a full arrowhead to do this. And that would give us our second carbocation over here. So these are two different resonance structures. They happen to have the same energy, but we're going to see reactions in which these carbocations form and charges move around that can lead to having different products. Now, let's look at our reaction. So we're going to look at our first reaction of this chapter. It is selective bromination at the allylic position, otherwise known as allylic bromination. So the observed reaction here takes an alkene. So we have our alkene. We're adding bromine, and then we have light, and we're going to get a brominated carbon atom at the allylic position plus HBr. Now, as we go through, we're going to see that there's some problems here. So one of the things that we're going to see typically for this to react is an NBS down here. Okay, and remember that that position right there, just as a reminder, that's your allylic position. Okay, now do you remember what the mechanism is here for this type of reaction? Well, we haven't seen it exactly, but we see lights involved, so we might predict that this could be a halogenation. In fact, a free radical halogenation. So remember, there's 3 steps to free radical halogenation. That first step is initiation. So let's just write that down here. First we have initiation. So initiation is going to take bromine with some light, and then we're going to do this. Remember the fish hook arrows, right? And that will give us 2 bromine radicals. Okay? So initiation, next comes propagation. And remember, there's 2 steps for propagation. So there's step 1. So step number 1. So let's take a look at an example here. Let's take this molecule. Okay, now what I want to do is I want to put H's at that position. Okay. In our first step, we're going to take one of those radicals from up above, and one of those radicals, the bromine here, is going to swing over and it's going to slam into the hydrogen atom, and it's going to take that H atom away. Doesn't matter which one. I'm going to do it to this one here. So what's going to happen is it's going to swing over and crash into that, and we're going to see a transfer of electrons that looks like this. And it kind of looks weird because it looks like these electrons are just going off into space, but remember, bromine is coming over and taking the H away. Now, what that's going to give us here is this, and I'll just write that out as a CH2. It gives us this as a radical. Okay. And then leave some space here, and the other thing we get is HBr. Now, I want to leave space here because this has resonance. So we're going to draw out the resonance structure of this. When we do that, we put our arrows in just like that. And I'll write out that CH2 on the other side for clarity. But we end up getting this. Now those 2 structures are going to lead to the same product, but they're not always going to do that. So we have to take a look at those resonance structures. If they were different, then we would write out propagation step number 2 for both of these intermediates. So let's move on here to step number 2. So let's grab one of those guys. And I'm going to go to line structures right now. So we'll do this. And then we're going to add to that bromine. Now remember, in propagation step number 2, we need to regenerate the radical, right, so that we can have that propagation step happen over and over and over and over again. So what's going to happen is bromine's going to come over. We're going to grab a hold of that radical and create another radical here. So that's going to give us this plus the bromine radical. Now, that radical then can feed back. So this guy here can feed back, right, over here into our propagation step number 1. So what happens, initiation in theory happens once, and then you get about 10,000 propagation steps for that. And propagation would continue on and on if it wasn't for step number 3, which is termination. So in termination, all radicals combine. So the radicals that we have here, and I'm not going to write out every one of these things, but this, right, plus bromine radical. We could also do that plus this, and we could add bromine plus bromine, And remember, the other thing that your book talks about is that these can hit the glass wall, right? So the glassware itself can capture those radicals. All right, now there's a couple problems here. So let me pull this thing down here and let's take a look at it. So, problems. The bromine can add across the double bond. And so if you recall from chapter 8 last semester, if we add bromine here, what we can get is we get a bromine added here, right? And then a bromine added here. And then that would be a chiral center. So you get more than one product there, but you get it added across the double bond. All right, so the solution here is to use a low concentration of bromine. So if we use a low concentration, then maybe we can stop that from happening. Now, the other thing that happens is during the course of this reaction, and also in the observed reaction, you may have noticed that HBr is formed. So the other thing that happens here is that we can add HBr to a double bond, and it reacts pretty quickly, right, to form this. Right, so that's the other issue. So what we need is we need to have a low concentration of bromine, and we need to somehow control the HBr being formed here. Right, so let's take a look at how we do that. Now, what we're going to do is we're going to use a chemical called Inbromo succenomy. Right, now, what NBS does is a couple of things. So looking at it first, and let me just draw it up here for you guys so I can put this in for you. So N right, so get that in there. That's your Inbromo succenomy. What happens is that when you just have a bottle of this and you have a little bit of light present, you get the following reaction occurring. So we get this. Right, now let's put in our lone pair there on that nitrogen. Right, that's going to give you then nitrogen. Right, with our double bonded oxygens and a radical here, right, plus the bromine radical. So this is going to give us here a low concentration of the bromine radical. So that's one of our requirements. Right, so the first thing here, we may even make a note. Here's how we get a low concentration of, well, really, the bromine radical, right? Okay. And then the second thing is that we want to consume or limit the production of HBr. So when you look down here at your NBS and add HBr, the NBS consumes your HBr, and it also gives you this kind of low concentration of Br2 here. So there's your Br2 also that can get cleaved for your free radical reaction, but it's produced in low quantities. Right? All right, now let's look at an example here together. Let's see if we can figure out what happens here. So let's take this molecule here, and let's see if we can predict what the products are of this reaction. So what you're often going to see is NBS in light, just like this. Right? So remember, what happens here is that we want to predict the products, okay? So just on a scratched piece of paper down here below, we're recognizing, aha, that is your allylic position. So that's where we're going to form our radical. So we are reacting this. Right? So that's the thing that forms there. Right? So what happens, right, is your Br radical comes in, takes one of these guys off, and down here you have HBr, right, mechanistically. So what we're dealing with is this. Now that has resonance. So going through and drawing some resonance of this thing, right, we're going to do this and that, move that down here. And then our other big resonance that you want to make sure you get is this guy. Now it turns out that there's one more. So in this original structure up here at the top, we have free rotation around this carbon that's circled here. So in other words, some of the times this molecule can adopt that conformation. And if it did that and we end up with a radical here, then the other thing that we could form down here below would be our double bond in the middle, but this kind of cis orientation. So if we're being perfect, then we could form all three of these things. The first two being more important than the last one. Now, that's your step number one. Your step number two is going to take each one of these. I'll just draw an arrow out like this, and it's going to add Br2, because that's your propagation step number two. And the end result is that we're going to brominate the carbons that have those radicals on it. Now, let's take a look at this. So remember from first semester, hybridization right here, sp2. This is sp2, and obviously that's sp2 also, right? So when we come in with our bromine, that electron, it's residing in a p orbital that's either pointing at us or away. So for our first product here, that carbon, if the bromine comes from the front face, where we're writing, then it's going to put that bromo group out here on a wedge. If it reacts from behind, it'll put the bromo group on a dash then. That happens all the time. It's up to us to figure out if the products are identical. And here they're not. Right? Now, this carbon is a CH2. We don't have to worry about chirality there because there's already two identical groups. So we're going to get a bromo here and then connect it down to where that radical was and have our double bond out, just like so. And then the same idea with this last structure. So bromo group here, connect it to our radical, coming up, down, and then putting our double bond just like so. So we'd end up getting, in this case, a total of 4 products. Now, one last thing to note here is that sometimes there's some regiochemistry involved. So this is what you're going to see most of the time. But sometimes you're going to see situations in which they ask you for the major product, for example. So if you were starting off with something like this, if we just create an alkene over here, do that, right? And if we were to add Br dot here, right, our radical, so the first thing that you'd form is this guy down here below, right? Because that's your allylic position, so you're going to take it off from right there. Okay. Now this has resonance, has other resonance structures and stuff in here too, so we can get cis and trans and stuff, but that would put our radical here in the middle, right? So what I'll do down here below, just to make this complete, is let's just write etc., right? Some other resonance structures too. Okay, but that's not the point to draw them all out. The point is to show, just looking simply at these two, which would be your predominant species. So in this case, that is. And the reason why this is going to be predominant is because we have conjugation here. Right? We see the same thing in like benzene type rings also. So you might see a situation where we have something like this and a radical here, and that radical can move all through the ring. Right, so we can do this. And I'm not going to draw them all out. That's a resonance kind of problem to do. So if you need to review that, do that. But you're probably feeling pretty good with it. So that would give you a radical there, and again, etc. But what happens is that we never react in that ring because we would destroy that the conjugated double bond system in that ring. Especially in benzene, they're really, really stable. So in this case, it would really only react here.